Welcome to this lecture in which we are going to continue our study of Chapter 4, the material point in 1D. And as promised, today we have to start discussing the dynamics, so the evolution in time. We have already discussed the description of the states with square integral functions and the main operators, position and momentum. But today we are going to have to describe the Hamiltonian or the Hamilton operator, which generates the dynamics. Now, we know from classical mechanics how the conjugate variables x and p enter the Hamiltonian for a material point. In one dimension, the Hamiltonian would be simply kinetic energy plus potential energy. And that's how the Hamiltonian will look like. And let me start from the very beginning, stressing that the different dynamics will, of course, be determined by the different potentials. So the shape, the form of this function of x will determine whether this is a free particle, harmonic oscillator, hydrogen atom in 3D, or anything else. The kinetic part is always the same. Let's see what this operator looks like in position representation. Right? So the h on psi, well, what is it? Integral dx x. Now this h, so I will put the x later just for sake of the argument. We have to write this operator in position representation. Remember that P in position representation is minus I h bar d over dx. So we will have the operator minus h bar square over 2m d square over dx square. This minus comes from the I square, minus I squared, and then plus v of x. This is a function of x, therefore, as in position representation, is just that particular function on the number x, on the real number x. All these things acting on the wave function, and then this pseudo vector. And so this operator is the Hamiltonian in position representation. In the lecture notes, I have systematically written it h in the index x, where this index again represents position representation. In all textbooks, this x is not there. That's just a pedagogical trick that I invented in order to distinguish the Hamilton operator as an operator on the Hilbert space from the differential operator that acts on the wave functions in position representation. But I repeat, no textbook ever will use this notation. And I may myself sometimes call this thing just h instead of h of x. In the lecture notes, I think I've been systematic, at least in this chapter, to call it h of x, this particular object. Now, you remember what we want to do with the Hamiltonian. We had this famous recipe to solve the dynamics, is to diagonalize the Hamiltonian, find eigenvalues and eigenvectors, and then to decompose the initial state onto the eigenvectors of the Hamiltonian. And once we have that, we just add those phases that are time dependent with the energy in front on the decomposition of the vector. So I told you when we were studying this in general that for finite dimensional systems, the diagonalization of the Hamiltonian is always possible, maybe with the help of a computer, because this is a finite matrix. So the Hamiltonian will be a finite matrix. Of course, if it's 5 by 5 or 10 by 10 or 200 by 200, probably by hand is not feasible, but a computer can always find a solution, and at least the solution we know it's always exists in a closed form. However, the solution of this equation, h psi equal to e psi, that's the eigenvalue solution for the Hamiltonian, may not be feasible to find in exact form, not even with a computer, when the Hamiltonian is a differential operator. How does it look like with this guy? Well, let me write it explicitly. We have to solve this differential equation minus p square plus v of x acting on psi of x must be proportional to psi of x. Sometimes this object is called the time-independent, or the time-independent Schrödinger equation. Historical name, I find it confusing, is just the eigenvalue equation for the Hamiltonian, right? And the name comes from the fact, I repeat it again, that once we solve these, the dynamics is fully solved. So essentially the Schrödinger equation is fully solved. Okay, so this is something we are going to set out to study in detail. Now, first I will give you two generic results on the dynamics, and later we are going to start studying some specific examples of potentials. The first generic example that generic topic that I want to deal with, maybe I should erase something, is what is called the continuity equation. So, let me tell you what that means. You have something similar to continuity equation for the wave function. You have a continuity equation, probably you have seen it in electromagnetism, and this continuity equation tells you that electrical charge cannot disappear from here and appear there instantaneously, right? That the motion of electric charge is continuous and is described essentially by the electrical current. So here we have exactly the same idea, that if I have, let's say, a wave function that is localized here, I cannot instantaneously, just the following delta t, have something that appears there. And maybe, I don't know, maybe disappears from here. We cannot have some amplitude of probability appearing at a distance. It tells that the wave function will deform itself in a continuous way. So this may happen later, but there must be a movie somehow, a continuous movie that goes from the first wave function to the next. And so there is a current that describes this. It's a current of probability now, it's not a current of charge, that describes that this continuity of the evolution of the wave function. Let us prove, this is not a statement, it's a theorem. Let us prove that this current actually exists. So the continuity equation in general is something of this type. d over dt of the density plus the divergence of the current. The divergence in one dimension is just the derivative with respect to x. Is what is usually the charge. Here there's no charge, there's no source of the wave function, so is 0. This is a continuity equation. Density of charge or density of probability here, density of current is equal to the sources. Okay, so let's try to take d over dt of rho of x. What is rho of x? You remember it's the square, modulo square of the wave function. This is d over dt psi of x squared. Well, this is psi star times psi, symmetric. Of course, these are just numbers, so they commute. So we have d over dt, let's see in which order I wrote it just for convenience, psi star of x multiplying psi plus psi star of x multiplying d over dt psi of x. Now, good? Now we know what this is. But this is what gives, it comes from the Schrödinger equation, right? This is I h bar times this is equal to h times psi. So this is I minus I over h bar. H, and I'm using this h of x, psi of x. This is just the adjoint of that. The Hamiltonian being self-adjoint is this, is I over h bar, h of x psi star of x. Okay, so what do we have? Well, here, let's open it up. Let me just forget for I over h bar for a moment. So I will open up this guy. There is this minus h bar square over 2m dx square psi star plus v of x psi star correct? And this one, of course, would be the same with psi. Minus h bar square over 2m d square x psi plus v of x psi. Now, you see what happens here? Probably you see that this term, what is it? There is a v of x psi star psi I over h bar, and this one there is a v of x psi psi star, which is the same, minus I h bar, so these two terms will cancel. And we are left with something that does not cancel. Why it does not cancel? Because here we are taking the derivative of psi star, and then multiply by psi. And here we're taking the derivative of psi, and then multiply by psi star. So what we're left with is something that looks like I h bar over 2m, then the double derivative with respect to x of psi star. Well, maybe I write it slightly differently. I will write psi of x, double derivative with respect to x of psi star, minus psi star of x, double derivative with respect to x of psi. And now, you see what we want? We started from here, and we want these. So we would like this guy to be equal to minus d over dx, j of x, and I let you check. You can check it rather easily that this is the case if it's okay, correct, for the following expression, j of x equal to, I never remember this one by heart, so you're forgiven also if you don't remember it by heart. It is psi of x dx psi star minus psi star of x d of x psi of x. Okay? I don't pretend that there is an entirely intuitive explanation for this object. We are going to use it later when we do the potentials with piecewise continuous. But what we proved so far, anyway, is that indeed there is a continuity equation. This is the current. And so therefore, the probability distribution cannot disappear here and appear there instantaneously without a continuous change between the two. If you wanted to say dramatically, this means that in quantum mechanics there's no teleportation of matter, right? Matter cannot disappear from here and appear there. We have seen in 6 quantum pieces that there is teleportation of states, but the matter must already be there. Excellent. The second topic I want to discuss is what is called the Ehrenfest theorem. It's presented in different ways in different textbooks. I will do a presentation here that involves a notion that we have not really practiced, and we are not going to practice too much. Actually, we're not going to practice at all. But it's useful to remember, and it's probably the most elegant way of presenting this Ehrenfest theorem. So what is it? Well, let me just a small reminder of something that I discussed at some point in chapter 2. It's called the Heisenberg picture. And if you remember what it was, otherwise you look back at it, the Heisenberg picture is the fact that we normally look at the states as evolving and the operators being fixed. But we could also look at the operators evolving and the state being fixed. So the Heisenberg picture is the one that we normally don't use in this course, which is the situation where the operators evolve and the state is fixed. But for this theorem, you will see that it's very convenient. It gives a lot of physical insight to see what is happening if I go into the Heisenberg picture. So, and if you remember, in the Heisenberg picture, the Schrödinger equation became something like I h bar dA in a Heisenberg representation, or dt, that's the operator. This was equal to the commutator between AH and the Hamiltonian. Okay, so let's do it with position and momentum. I will drop this index that says Heisenberg, so please remember now that position and momentum in this calculation will be done in the Heisenberg picture. So, I h bar dx over dt is the commutator between x and the Hamiltonian. What is the Hamiltonian? Is p squared over 2m plus v of x. Now, the commutator is linear. So this is the sum of two commutators, the commutator of these with that, plus the commutator of these with that. Now, this is a function of x, and so it commutes with x. So the second term is 0, and we get these. By the way, I can take out, just for fun, 1 over 2m, and I have commutator of x with p squared. Not too difficult exercise using A commutator BC is equal to whatever it is. You find in some tutorial. This, again, is good practice for you to find that this is equal to, this one is equal to I h bar p times 2. And the 2 disappears, so we've got this. But now, look what we have written here, I h bar dx over dt. So this is an exercise, if you want. I h bar dx over dt is equal to I h bar p over m. What have we found? Well, something that doesn't look completely unfamiliar. We have found that dx over dt is p over m, which in classical mechanics would be v, right? So this looks like, hey, this quantum Schrödinger equation, it behaves like the Newton equation, right? Like the normal Hamiltonian dynamics. Well, we have only one of the two, however. Let's try with the momentum operator. This one is a bit longish to do. I mean, it's one of these things that you have to be careful. So, I h bar dp over dt is equal to commutator ph. Again, this is equal to commutator p squared over 2m plus v of x. These two commute, so this is equal to commutator p over v and v of x. And now you may think, well, now we are a bit in trouble because v of x can be absolutely anything. So how am I going to compute this commutator? I don't know what kind of function it is. But if we pass in position representation, that's not too difficult to compute. So let's go in position representation. What is p? So this commutator is minus I h bar d over dx p v of x, and then minus v of x minus I h bar d over dx. That is this commutator. And now, before we make a silly mistake, let's remember that this is an operator. So it's supposed to act on a function. And this is interesting to see. So this guy is supposed to act on a function. But what does it mean? You see here, this is not the derivative with respect to x of these. So this term should be read as d over dx of the product. Right? Because if you look at what the operator is doing is first multiply v with f and then take the derivative of what is left. Whereas here we have take the derivative of f and then multiply by v. What is this? Well, this is obviously v prime of x f of x plus v of x f prime of x. And this is f prime of x like this. So these two terms will cancel. You can do it quickly. And you will find that this is equal to that. V prime of x, f of x. And by identity of the operators, because these two operators are, sorry, there's a minus, there's certainly a minus sign somewhere, right? Let me see where, if I got the minus signs correctly. There is a minus IH bar in front, sorry for that. Minus IH bar in front there. So, you see, now, because this is true for every function f, this operator is equal to that thing. And so here we have minus I h bar v prime of x. So this is the operator that is obtained by, so what is this operator? What this operator is, v prime of x, is the following thing. Take the classical expression of the potential, v of x, compute the derivative, v prime of x. I don't know, if this is x cubed, this would be 1/3, 3 derivative, not integral. 3x squared, really like that. And now, once you've taken the derivative, replace the x with the operator, and you get this object, okay? So what we've got here, again, there is d over dp v prime of x. We have found something that looks pretty much familiar. dp over dt is equal to minus v prime of x. So, hey, it seems that there is something funny here, right? It seems that when we look at the evolution of the operators rather than the state, the Schrödinger equation is exactly the same as classical mechanics. That may sound bizarre. Actually, it's not bizarre at all, right? I told you at the very beginning of the lectures that the main difference between classical and quantum is not in the evolution, is not in the Schrödinger equation, is in the way we describe the system with these operators and states and Hilbert spaces. And this is a pretty clear evidence that what I'm saying is kind of correct. By the way, there's no H bar into that. So it seems that it's really a result that classical and quantum hold the same. However, and now comes the interesting thing, there is a difference between classical and quantum evolution. Let me show you how. When we come to measurement. So I will keep the equations there. And I'm going to ask the following interesting question. So, given a state psi, is it the case that the average values of x and of p evolve, maybe not a very precise statement, evolve like the x and p of a classical particle in the same potential. So can I just say that if I look at the average position and average momentum, their trajectory in phase space is exactly the same as I would have for a classical particle in that potential? Well, let's try that. Let's try it here, right? Well, taking the average value commutes with the derivative because the state is fixed, right? The state, here is the operators that evolve, the state is fixed. So we have that dx over dt is equal to p over m. So far so good, this looks pretty okay. Let's try the second one. dp over dt is equal to minus average value of v prime of x. That in general is not equal to minus v prime evaluated in x. I don't know if you are clear with that. Let me do it very simply, right? If you have any function of a random variable, right? The average of f of x is usually not f evaluated on the average of x. In fact, it is usually the case, apart from maybe pathological cases, if and only if f is either constant, so f of x is equal to a constant plus a linear term, right? Because in this case, f of x would be a plus b x, which is the same as f of x. And so if you look what this means for a potential, our function here is the derivative of the potential, so it would mean that this is equal to minus v prime of x, essentially only if and only if, v of x is at most quadratic, a plus bx plus cx squared. As soon as the potential has a cubic term or a cosine term or anything that is not a parabola, these two expressions are not equal. So the answer to this question is no. No in general. But sometimes yes. Sometimes yes, depending on v. If v is quadratic in particular or linear, then it is the case. Okay? So there is some difference between a classical dynamics and a quantum dynamics, but are not extremely deep. And where do these differences come from? From the description. The equations look the same, but because these equations apply to operators and not to numbers, and we have to evaluate them on states, then the average of numbers do not follow the same laws. Okay? That's a quite deep result called Ehrenfest theorem. And with this I finish all that I wanted to say about the generalities of the dynamics. Now let me move to the first example of dynamics. It's kind of trivial. You will see what's going on. And it's what is called a free particle. So, case study. First case study. Free particle. Definition. V of x is equal to 0. Right? So, nothing simpler that you can expect is the particle that is not submitted to any force, any potential, it's just kinetic energy. You know what to expect from classical physics, right? The particle doesn't move. Wrong la. The particle keeps the same speed, right? Inertia. If the speed is 0, it doesn't move. If the speed is fixed, it keeps the same speed, it goes linear motion. right? That would be the classical prediction for only kinetic energy. And we're going to see that the quantum mechanical, again, is essentially the same. There is a bit of trick when we look at the wave function. Now let's see what we can say here. Okay, so remember that we want to solve the dynamics, but let's go calmly through it. So now we have the Hamiltonian is equal to p squared over 2m. Before even I do any calculation or any attempt, so then this would be that hx is equal to minus h bar squared over 2m, double derivative in position. Okay, before I do absolutely anything here, I know that h commutes with p. But if h commutes with p, then momentum is conserved. And in particular, so all the statistics, in particular, this implies that the average value of momentum at the distribution of momentum is conserved. So average value of momentum at the power n at time t is equal to the same value at time 0 for every n. Now let's go back to Ehrenfest's theorem. That's the first point. Second point, from Ehrenfest's theorem we know that we have P of t is equal to P of 0, right? But the Ehrenfest theorem was telling us that dx over dt is 1 over m times p. This at any time. But momentum does not depend on time, so this is equal to p of 0. And now we have a very trivial differential equation, which is the derivative of this function of t is equal to a constant, right? So from here, we immediately get that x of t is equal to x of 0 plus this object times t. That's usually called speed. So obviously, in this case, the Ehrenfest theorem applies very nicely, and we see that the average position indeed is just that of a particle moving with constant speed in the one dimension as we are considering. Well, now let's go through the motions of actually solving the full Hamiltonian by the usual technique. So now, so all the dynamics, well, what do we need to do? We need to solve, well, h psi equal to e psi first, right? And so what is this? In x representation is minus h bar square over 2m, double derivative with respect to x of psi of x is equal to e psi of x, right? And what do we know about E? Well, E cannot be negative because the Hamiltonian is a square. That is not, maybe not entirely evident from here, but so we know that we look for the constraint is that E must be positive. An Hamiltonian that is a square cannot have negative eigenvalues. So when we move to that's a bit of a tricky step, right? When we move from the Hamiltonian to the differential equation, some things may be lost in transaction, and you must be careful to remember them. For instance, here, this differential equation, strictly speaking, just if I just throw you these without telling you anything, it looks like it can have also, it has some solutions for negative E. This would be something like hyperbolic cosine and hyperbolic sine, or exponential increase, exponential decrease. But of course, this one would not be nice solutions, would not be square integral functions. Neither the ones with positive E, but these ones at least are under control. These are one of these plane waves, right? So I need to impose that E is positive because I know from the beginning that the Hamiltonian is a quadratic operator. And so what is the solution here? Well, for every E larger than 0, there are two independent solutions that are psi plus or minus, what did I write it here? Well, I should write a E of x. So for every given E, I have two solutions that are given by, well, a constant that I don't care, and then E plus or minus ikx, where this k vector is simply square root of 2me over h bar. And if you invert this one, you get the famous relations E is equal to h bar square k square over 2m. And by the way, you can check that these, what are these? You remember what they are, right? These are also the eigenstate of momentum, which is not surprising because it commutes with momentum, right? It's a function of momentum. And the momentum, so this guy, this would be actually equal to psi plus or minus p of x with p equal to h bar k. And k is related to this, right? So we can parameterize these solutions with the energy, but because it commutes with momentum, we can also parameterize with momentum, and you can check that indeed these are the solution of momentum if I write k is equal to p over h bar. Okay, very nice. So we have the and then for all E. For all E strictly positive. Of course, if E is 0, then it wouldn't work. So what do we have? Oh, we have the eigenvalues and the eigenvectors of the Hamiltonian. We can solve the dynamics of every state. So let's do it. An arbitrary state, initial state, psi of x t equals 0. Well, I can always write it in Fourier transform, right? Psi tilde of k eikx dk. And here I have my eigenfunctions. I forgot about the constant. That usually we write this with a constant 1 over square root of 2 pi. It doesn't really matter. I mean, let's just make it proportional to. And so our recipe says that psi of x for any time will be equal to, again, proportional to integral on the reals. The coefficients don't change. And this fellow gets, let me write it in red, gets its energy. So e to the minus I e t over h bar eikx dk. And now what is E? E is written down there. So I will just erase it peacefully and say, write it whatever it is, which is minus I h k square over 2m times t. I will just replace the energy there. All right. And now if you look what that expression looks like, this looks like ei kx minus omega t for omega of k, well, is this h bar probably k square over 2m. This is what you would call a dispersion relation in optics, is the dependence between the wave number and the frequency of the wave. So, well, I mean, that's nice, right? Now, what is it? Well, now it depends on what these coefficients are. You give me these coefficients, so decompose the initial state into the basis of the eigenstates of the Hamiltonian, and then, well, that's what it is. I know, depends on the example, right? There is a famous example in the literature that is dealt with in detail. It's the case of a Gaussian. I will not do it here. It's super boring, and you find it in every textbook. So if someone wants to practice it, please go ahead. You will find all the calculations detailed there. So that's the case of a Gaussian. Famous example. So special case, I will just give you the result. The special case is when psi of x 0 is a Gaussian, so something like e to the minus x squared over a squared, which means that psi tilde of k is something like e to the minus, and probably there is a 2, probably is a k squared over, if I put a 2 here, there is a 2, sorry. If I put a 2 there, there is a something like that. All right, so it's also a Gaussian, the proportional 2, again, there's some constant. And then what happens here? Well, so you have an initial wave packet that looks like that, and it's moving, the center is moving with speed v times t. And v is just p over m times t. That's the center of mass. However, the fact that there is this object deforms the wave, and so when it's here, it turns out some deformation has happened, and in particular, it's become broader. And you can prove that this delta x of t is equal to something like that, d times 1 plus h bar square over m square d4 t square, where d is actually the initial value of the spread. So this would be d, and this would be that. And you see that this number being bigger than 1, it grows more or less linearly in the long term. At the beginning, like a square root. Okay, so you see that, so the classical motion, the motion of the center of mass is classical, but there is something happening that is properly quantum due to this wave behavior, is that the particle, if you want, spreads. Now, just before I finish, let me remind you that this is an extreme idealization, right? Because this free particle is something that, I mean, in a lab, at some point you hit the walls, right? So, and there are all kinds of potentials going on, gravitational potential, containing potentials of the wall, and so on. So this is a kind of very special case, but it already gives you a little bit of feeling, right, on how to deal with wave functions, how to use our famous recipe that the Hamiltonian, once we have the diagonal version, we can solve exactly the dynamics, and that the dynamics is not too different from the classical one, but there are some subtle differences. So the next lesson will be about what is called piecewise continuous potentials, and there's a whole mathematical technique to deal with them that we are going to study in detail. You can stop watching now.